And now, once we've defined a type class with some propositional content, we can use it for proving other things. So for example, if x, y, and z are elements of type A, where A is an instance of EQDEC, then we can show that equality is transitive. Sorry, we can show that if x and y are judged equal by the EQB function and y and z also, then x equals z. So this is kind of transitivity modulo changing from Boolean to propositions. And we do it by rewriting using the elements of the evidence that we were given for the EQDEC class. All right, let me pause and see if there are any questions. Please.
Equality is well-known proposition. What about something user-defined? So let's say we want to define our own equality, we have to somehow add it to the type class. Is that possible?
Yeah. So the question is, here we were doing something with equality, which is a built-in thing. What if we wanted to do it for something user-defined? Well, we are doing it for something user-defined, namely the EQ type class. So we're already halfway there. But I guess my answer is everything we're looking at here extends totally smoothly to user-defined types. So if you want to replace, equality by some computation on colors or whatever, that will just work.
And you could also make the notion of equality be a member of the type class, or you can make it be a parameter of the type class?
That's right. So Adam comments that you can make the notion of equality be a member of the type class or a parameter to the type class. So there are lots of ways of parameterizing these things to get more generic behavior. Please.
Can I have multivariable type classes in Coq?
Can you have multivariable type classes? I believe the answer is no. Maybe somebody is expert enough to say if I'm wrong. Nobody is saying I'm wrong. No. But one more question.
When you use the combinator for the show type class, it inferred the instance, or it generated it. Will that put it into the type classes database?
Good question. So when we use the instance of show with a complicated type and therefore had to search for it, did that instance that was found go into the database somehow? No. If we need it again, we'll just search for it again. Other questions? Yes, please.
So is it possible to use hint to add stuff to the type class instances database?
Excellent question. So can you use hints to add stuff to the type classes database? Yes. And that is often super useful. So if you have a complicated development, it is frequently useful to kind of curate the type class hint database. So you can add hints to it and you can remove things from it. Please.
So type classes are actually an extension to the Coq type system.
So type classes are an extension to the Coq system? No, not really. They're an extension to certain aspects of Coq's implementation, but they don't extend the fundamentals of the type system. In other words, there is some, they extend the type inference engine by adding this kind of auto-based search. But they don't extend the logic certainly at all.
Right. So actually, it's on top.
It's completely on top. It's a layer on top.
So does that mean that other type system features can be also added on top fundamentally?
So does that mean that other type system features can be added on top? That depends on the feature. Other last questions? Okay, so let's go on. We've looked at the show type class and the EQ type class. There are a whole bunch of other useful type classes that are very handy for programming in Coq. Here is one. It's a little bit like EQDEC, but but more general, because it isn't only talking about equality, it's talking about any kind of decidable property. So, and for this we rely on a definition from the SSReflect library called decidable. So a decidable proposition P evidence that a proposition P is decidable is a proof of P or a proof of not P. And this evidence has the special property that it is an informative disjunction. That is, you can test it in programs. So you can write when you extract Coq to ML, for example, you can use decidable properties as if they were Booleans. Okay, so that was the decidable definition from SSReflect. Here is the DEC type class. So DEC is a type class that whose instances are propositions with a DEC method of type decidable P. In other words, P is eligible to be an instance of the DEC type class if we can define something of type decidable P. So it shouldn't surprise you to know that if something is an element of the EQDEC type class, then we can also make it an instance of the DEC type class. And here is a little proof that that's the case. Here's a fun one. It says, if H and I, if P and Q are both decidable propositions, then P and Q is also decidable. This is not surprising, but it's useful to write down because it means that the type class inference mechanism can come into play when we're asking to construct decision procedures for various logical propositions. And then last bit of convenient syntax is if P is a decidable thing, then we can write P question mark to get from the proposition P to a Boolean that's true if P is a true proposition and false otherwise. So what this means is that we can write down logical statements inside of code and then just put a question mark after it as long as the statement is decidable. And this is quite convenient because, as you've seen already, in Coq, one often kind of shifts back and forth between the Boolean world and the propositional world for different reasons. And being able to write things like this means kind of cuts in half the notational overhead of having to remember the names of everything in the Boolean world versus the propositional world. You can just remember it in the propositional world and convert to Boolean when you need to. Okay, so that was the DEC type class. Here is the monad type class. As soon as you heard the word type class, those of you that are Haskellers, I'm sure you knew that monad was coming. And monad is indeed extremely useful in Coq programming, just as it is in Haskell programming. It's particularly useful in situations where we want to do effectful things like I/O or state mutation or things like that. Of course, we don't literally do I/O or mutate state in Coq, but we do often write Coq code that extracts to Haskell or ML code that does do those things. And the I/O monad is a nice way of structuring and notationally lightening that code. And then there are other things that we want to do that, there are other effects like failure, non-determinism, randomness, and so on. Randomness, of course, we're going to use heavily for quick check. And then other things like programming with options and lists and things like that, that Haskell programmers know are often quite convenient in monadic syntax, although they are pure. Okay, monads are such a popular concept that there are not one but several Coq libraries for programming with monads. You can take your choice for your own developments. For this development, we've chosen one of the popular ones, which is Gregory Malika's monad code from the xlib library. So here's the main definition. It's a type class called monad. It classifies not types, but type families. So it classifies M's, which are functions from types to types. And in order to be a monad, a type family M needs to have two operations defined on it called return and bind. And at this point, I think, since most people have probably seen this before, I'm not going to do a big song and dance about exactly what these things are. Those of you that haven't seen monads, there are 1 million, that might be an exaggeration, maybe only 100,000 tutorials about monads that you can easily find online. In the chapter, we have references to a couple of good ones. But you can easily learn about what monads are and how to use them. So I'm going to kind of skim over this and just show you some examples. So here is the option monad. The return in the option monad just takes a value and wraps it in the sum constructor. The bind of the option monad takes a value from a previous computation, which should be an option. If the option is none, then it simply returns none. If the option is sum of something, then it applies a further value, a further function f to that thing. And what that means, and those of you that are Haskellers might have been worrying about, do I have to write down ret and bind all over the place? No, we can use the notation mechanism to introduce lightweight syntax for monads, just like Haskell has. So instead of writing bind M1 and then lambda x M2, we can write x left arrow M1 double semicolon M2. Why do we need the double semicolon? Because single semicolon is used in lots of other places and creates parsing hassles. So we use double semicolon. And if we're not interested in the value from the first one, if we're only running M1 for its effect, we can leave off the x back arrow and just write M1 double semicolon M2. Okay, so now we can write, we can simplify plumbing as one does with monads. So for example, if we have an nth opt function, we saw it the other day in the tutorial, that takes a number and a list and returns the element of the list at that index, or returns none if the list doesn't have that many elements, then we can write a function that extracts the first, second, and third elements of a list and sums them up, returning none if the list doesn't have that many elements, in a really clean and lightweight way. So all of the plumbing that says, well, does this actually return none? And if so, then skip all of that and immediately return none. All of that is hidden in the monadic syntax. Okay. Another convenient thing with programming with monads is being able to lift values to lift functions, from operating over values to operating over monadic things. So lift m takes a function f from t to u and lifts it to m of t to m of u, where m is a monad. And again, this is just like in Haskell. And lift2 takes a 2-argument function and lifts it into a monad. And there's also lift3 if you want it. So, for instance, we can write our, I guess this is only sum2. We can write our sum function just by lifting plus into the option monad. Okay. There's lots more to say about monads, but it's really all the same as in Haskell. So I'll answer a couple of questions and direct you to Haskell readings for more, please.
In the monad type class, did you make it necessary to have a proof of monad law?
Excellent question. So are we required to prove the monad laws in order for something to be an instance of the monad class? No. So even if we were proving everything, it is frequently useful to use monadic syntax and notation, even for things that aren't monads, that aren't really monads. They're just morally monads, or we like to think of them as monads or whatever. And sometimes there are things that are not monads kind of on the nose, but they're monads up to some equivalence, or monads in some more complicated way. So the xlib library breaks things up. So there's the monad class, and then there's another class that I forget the name of for kind of provably monad, where you do add the proofs in.
Is there no applicative functor in this library?
So the xlib infrastructure does include a whole bunch of stuff like applicative and functor and so on.
But it's lift and two, is it then?
And we are not making full use of it here. Just to keep the tutorial simple. Other questions? Okay. All right. One thing to realize and be careful of, because it will bite you, I promise, is that the type class inference mechanism can sometimes do a little too much. Here's an example. Suppose we define a function foo that tests whether its arguments are equal, tests whether its argument is equal to itself, and then returns, of course. Now, we can apply foo to arguments from any equality type, I suppose. That's what type classes should be giving us. So can we really? No. If we apply foo to true, what we will see is the term true has type bool, while it is expected to have type bool-arrow bool. Where did bool-arrow bool come from? I'll tell you where it came from. So we defined foo. Let's look at the definition. We didn't declare any type for x. So the type inference mechanism had to find a type for x. Initially, it did that simply by filling in a unification variable and proceeding with type checking. The next thing that happened was we needed to find an instance for the EQ type class for that type. So we started searching. And lo and behold, we found something. In the hint database, it was the EQ bool bool function, which is the function that, for some reason, tests equality on functions from bool to bool. There happened to be such a thing in the hint database, and the search happened to run across it first. Since the type variable that was the type of x was completely unconstrained, the unifier said, oh, this looks good. Then later on,